Welcome to a journey beyond the limits of imagination. Out there in the vast darkness of the universe, there are objects so large, so extreme, that even our best understanding of physics begins to struggle. We've discovered stars that dwarf our sun, stars so massive they could swallow entire solar systems without effort. But among all of them, there is a growing mystery, a possibility that somewhere in the cosmos there exists something even bigger, a star so enormous it shouldn't exist at all. Some astronomers have begun to refer to it as a behemoth, not because it has an official name, not because it has been fully confirmed, but because the idea itself demands a word that feels almost mythical, something that represents scale beyond reason, something that forces us to ask a simple but unsettling question. What is the largest star in the universe? And more importantly, have we already found it? At first, this might seem like a straightforward question. After all, we measure stars all the time. We calculate their size, their mass, their brightness, their distance. We've mapped galaxies, observed black holes, and even detected gravitational waves from collisions billions of light years away. But when it comes to the largest stars, things become far less certain. Because size, in space, is not always what it seems. A star can appear enormous simply because of how its outer layers expand. Another may be more massive, but more compact. Some stars are constantly changing, swelling and shrinking over time. Others lose material so rapidly that their true size becomes difficult to define. So when we ask what the largest star is, we are not just asking for a number. We are asking how we define size itself. And that is where the mystery begins. Our own sun, for example, feels unimaginably large when compared to Earth. It is so big that over 1 million Earths could fit inside it. Its gravity controls the entire solar system. Its energy sustains life on our planet. And yet, in the grand scale of the universe, the sun is not special. It is average. There are stars hundreds, even thousands of times larger. Stars so vast that if they replaced the sun, their outer edges would stretch beyond the orbit of planets we know. Mercury, Venus, Earth, all of them would be swallowed without a trace. And still, even those stars might not be the largest. Because somewhere beyond the limits of easy observation, there may exist something even more extreme, something we are only beginning to understand, something we are not even sure we are measuring correctly. This is where the idea of the behemoth begins to take shape. It is not just a single star. It is a concept, a possibility, a question that sits at the edge of our knowledge and asks how far nature can really go. How big can a star become before it collapses under its own weight, before it tears itself apart, before the laws of physics simply refuse to allow it? These are not simple questions, because stars are not static objects. They are dynamic, unstable, constantly changing systems. Their size depends on a balance between gravity pulling inward and energy pushing outward. As stars grow larger, this balance becomes more fragile. The more massive they are, the more unstable they become. At some point, increasing size does not make a star stronger. It makes it weaker, more chaotic, more temporary. And yet, we continue to find stars that push these limits. Each discovery forces us to rethink what is possible. Each measurement introduces new uncertainty. Because the truth is, we cannot simply travel to these stars and measure them directly. We rely on light that has traveled for thousands, sometimes millions of years. We interpret that light, analyze it, and build models based on what we believe is happening. But light can deceive. Distance can distort. and our models, no matter how advanced, are still approximations. This means that when we identify a candidate for the largest star, we are often dealing with estimates, educated guesses. And sometimes, those guesses change. A star once thought to be the largest may later be revised to a smaller size. Another, barely noticed before, might suddenly appear far larger than expected. The ranking is not fixed. It is constantly shifting. And that is what makes the idea of the behemoth so compelling. Because it suggests that somewhere out there, beyond our current measurements, there may be a star that truly represents the upper limit. Or perhaps something that exceeds it. To understand how extraordinary this would be, we need to think about what size really means for a star. Unlike solid objects, stars do not have a clearly defined surface. Their outer layers are made of gas, gradually fading into space. This makes it difficult to determine exactly where a star ends. Different methods of measurement can produce different results. Whilst one method might define the edge based on temperature, another based on brightness, another based on density. Each approach gives us a slightly different answer. So when we say a star is the largest, we are choosing one definition over another. And that choice matters. Because in some cases, the difference is enormous. A star could appear twice as large depending on how you measure it. Now imagine applying that uncertainty to something already beyond comprehension. A star so large that even small measurement differences translate into distances greater than the orbit of planets. This is the scale we are dealing with. But there is another layer to this mystery. Even if we could measure these stars perfectly, there is still the question of whether such extreme objects should exist at all. Physics places limits on how stars behave. Gravity pulls matter inward, trying to compress the star. Energy from nuclear fusion pushes outward, trying to expand it. This balance determines the size and stability of a star. But as stars grow larger, their internal processes become more violent. Radiation pressure increases, instabilities form. Mass begins to escape into space. At extreme sizes, stars can become so unstable that they shed enormous amounts of material, preventing them from growing any larger. In some cases, they may even collapse or explode. This suggests that there is a natural limit, a maximum size that stars can reach before they become unsustainable. And yet, the candidates for the largest stars seem to approach and sometimes challenge that limit. Which brings us back to the central question. Have we already found the largest star? Or are we still underestimating what the universe is capable of? The idea of the behemoth forces us to confront that uncertainty. It represents the possibility that the universe is not done surprising us. That beyond our current observations, there may be stars larger than anything we have confirmed. Or that what we believe to be the largest may not actually hold that title. Because in a universe this vast, our perspective is always incomplete. We see only a fraction of what exists. We measure only what we can detect. And we understand only what our theories allow. Everything else remains hidden. Waiting. In the chapters ahead, we are going to explore this mystery step by step. These talks, we will begin by understanding how stars form and what determines their size. We will look at the largest stars we already know and compare their scale to everything familiar. We will examine the candidate known as the behemoth and question whether it truly deserves that title. And along the way, we will confront a deeper truth. That the question of the largest star may not have a final answer. Because the universe is not static. It is expanding, evolving, constantly revealing new extremes. Which means that somewhere, at this very moment, there could be something larger. Something we have not yet seen. To understand whether something like a behemoth can truly exist, we first need to answer a much more fundamental question. How big can a star actually get? At first, it might seem like there should be no limit. After all, stars are made of gas, and gas can expand outward into space without any solid boundary. But in reality, stars are governed by a delicate balance of forces, and that balance places strict limits on how large they can become. Every star begins its life inside a massive cloud of gas and dust. These clouds, often spanning light years across, slowly collapse under their own gravity. As the material falls inward, it becomes denser and hotter, eventually forming a central core where temperatures rise high enough to ignite nuclear fusion. This marks the birth of a star. From that moment on, the star is defined by a constant struggle between two opposing forces. Gravity pulls everything inward, trying to compress the star into a smaller and denser object. At the same time, nuclear fusion in the core releases enormous amounts of energy, creating pressure that pushes outward. When these two forces are balanced, the star remains stable. This state, known as hydrostatic equilibrium, determines not only the star's structure, but also its size. For smaller stars, this balance is relatively stable. Gravity is weaker, and the energy produced by fusion is moderate. These stars can exist for billions of years without dramatic changes. But as stars become more massive, everything begins to intensify. The core becomes hotter, fusion reactions accelerate, and the amount of energy pushing outward increases dramatically. At first, this allows the star to grow larger. More energy means more outward pressure, which expands the outer layers. This is why massive stars are often much larger than smaller ones. But this growth cannot continue indefinitely. As a star increases in mass, the energy it produces rises at an even faster rate. This creates a new problem. The outward pressure from radiation becomes so strong that it begins to counteract gravity in a different way. Instead of simply balancing gravity, it starts pushing material away from the star entirely. This is where the concept of a natural size limit begins to emerge. There is a point at which adding more mass to a star does not make it larger in a stable way. Instead, it makes the star more unstable. The intense radiation pressure drives powerful stellar winds, streams of particles that are blown off the surface at incredible speeds. These winds carry away mass, effectively preventing the star from growing any further. In other words, the star begins to lose material as fast as it gains it. This creates a kind of upper boundary. Even if a star forms from a very large cloud of gas, it cannot simply continue growing forever. The forces within it push back against further expansion, enforcing a limit on both its mass and its size. But size and mass are not always directly linked in the way we might expect. A star's size is not determined only by how much matter it contains. It also depends on how that matter is distributed and how energy moves through the star. Some stars are incredibly massive, but relatively compact. Others are less massive, but have outer layers that expand to enormous distances. This is especially true for the largest stars we observe, known as red supergiants and hypergiants. These stars have reached a stage in their evolution where their outer layers expand dramatically, creating sizes that are almost impossible to visualize. Their surfaces extend far into space, becoming diffuse and loosely bound compared to the dense cores within. This expansion happens because of changes in the star's internal structure. As fusion processes evolve, energy is transported outward in different ways, causing the outer layers to swell. The result is a star that can be hundreds or even thousands of times larger than the Sun in radius, even if its mass is not proportionally greater. But this expansion comes at a cost. The larger a star becomes, the weaker its grip on its outer layers. Gravity decreases with distance, and at extreme sizes, the outer regions are only loosely held in place. This makes them highly unstable. Pulsations can occur, causing the star to expand and contract over time. Massive amounts of material can be ejected into space, forming clouds of gas that drift away from the star. These processes limit how large the star can remain. Even if it briefly reaches an enormous size, it may not be able to sustain that size for long. It may shrink again or lose enough material to reduce its overall scale. This means that the largest star is not always a fixed title. It can change depending on when and how the star is observed. Another factor that complicates things is the definition of a star's boundary. Unlike a planet which has a solid surface, a star gradually fades into space. Its outer layers become less dense and less defined as you move away from the core. This makes it difficult to determine exactly where the star ends. Different measurement techniques can produce different estimates of its size, especially for stars with very extended atmospheres. This uncertainty becomes more significant as stars grow larger. For extremely large stars, small differences in measurement can translate into enormous differences in size. What one method defines as the edge of the star, another might consider part of its surrounding environment. This makes it challenging to compare stars directly and declare one definitively larger than another. So when we ask how big a star can get, we are not just asking about physics. We are also asking about how we measure and interpret what we observe. Despite these challenges, there are theoretical limits.